Hi, everyone. Thanks a lot for joining us at this Monster Scale conference today. My name is David Malinge. I'm a senior staff software engineer at ShareChat. With my colleague Ivan, we'd like to talk to you about how we built a large-scale feature store while managing costs today. So first, a few words about ShareChat. ShareChat is the largest Indian media network with more than 300 million monthly active users across our mobile apps. At the core of our product is personalized feeds. We're building state-of-the-art recommender systems to serve the best content to our users. The talk will focus on our feature store, which manages the data required to power these recommendations. So about the feature store, Monster Scale calls for a humble brag slide. We process more than 2 billion events daily to compute our features and serve close to 1 billion features per second at peak under 20 millisecond P99 latency. We also read more than 30 billion rows per day in Scylla, so we're very happy not to pay per use. Ivan will get back to this in a few minutes. Ivan already presented some of our work at the P99 CONF, so I will hand over the mic to him. Over to you, Ivan.
Hi, everyone. Indeed, on one of the previous P99 CONF, my colleague and I were talking about scaling our feature store to handle 1 billion features per second. We discussed various strategies to do this, like using Scylla, using smart data model, various optimizations, and other stuff. And we were really happy with the result. We were really happy that we managed to scale the system to handle the load. But once we presented the talk, our leadership came and said, great guys, like great system, but now please make it 10 times cheaper. And we like, what are you talking about? Did you just watch the talk where we discussed already how many optimizations we did? And they said, yeah, great talk, but you still need to make it cheaper. And so we started thinking about cost optimizations, and we realized that cloud cost is really complicated and confusing topic. For instance, like in billing, both AWS and GCP, they have around 40,000 different SKUs, which make it really hard to reason about the billing. And also providers are not motivated to make it easy to debug and understand. In fact, they're motivated in the opposite. And also it's easy to lose track of different components and running stuff. Like, for instance, you can forget some instance, you can forget some deployments, etc. And also the cost intuition for services is different for on-premise case and cloud case. And the system which may be cost efficient in on-prem might not be cost efficient on cloud. And even worse, a system which may be cost efficient on one cloud may not be cost efficient on another. This all make cost optimization is a tricky topic. And over our journey, we realized that cost optimization have the form of the funnel. On top of the funnel, there is something we call hygiene or discipline, which is basically just to ensure that you run only things that you need to run. You don't have any forgotten instances. You don't have any like buckets with unused data, or you don't have any buckets that don't have TTL when they should have. You don't over provision anything. And in order to achieve that, a crucial step is attribution. So every workload, every instance, everything should be attributed to the corresponding service and the corresponding team. Because once attribution is solved, the optimization becomes a local problem for the given team, which is much easier. Because when the team have the problem on hand, and they see the visibility about the cost items, they can work on optimizing them. So we did that, and this actually gave pretty nice cost saving, pretty big. In our case, it wasn't enough though. So we moved to another item of the funnel, which called cloud traps. Cloud traps is about something which you may face only in the cloud. You may not face it on-prem. And the first such item is cloud products. Cloud providers offer pretty nice and easy to use products, which easy to access and easy to use. And many of them have this serverless feeling. So you can just start using them and don't think about anything. It's pretty nice for the start. Although with the scale, it becomes painful in terms of the cost. Because many of these products have metered pricing either on the, like let's say, number of reads for the databases, on the number of traffic, this kind of stuff. And the cost naturally increase, and sometimes not linearly as you increase the usage. And the problem that you don't have any control of trade-offs. For instance, you may be okay to trade some latency for, let's say, cheaper hardware, but you cannot do this because you just only have this serverless thing. And so like when our scale increased, we realized that we cannot handle these cloud products in terms of the cost. And one thing that worked really well for ShareChat was the story to move to Scylla. We used different databases that GCP offered. Like we used Bigtable, we used Spanner, and at some point we realized that they became pretty expensive. And most importantly, they're out of control. We have very little leverage on the cost of this thing. And so we moved a lot of workloads to Scylla. It was a pretty nice and successful migration. More than 30% of Scylla cluster deployed across the org now, like in feature store is one of the use cases. And in addition to what Scylla usually offers, which is it's very stable database, very low latency, we've got a lot of control over our cost. For instance, we can play with different instances. We can merge some use cases to a single cluster, and we can use very high utilization of resources. Because Scylla works really well with like 80% utilization, 9% utilization, even 100% utilization. And so like we control what we want. And this gives us very nice cost profile for our Scylla. Another trap that you can face in cloud is called Kubernetes wastage. So in Kubernetes, like most cloud providers provide very good Kubernetes offering. And in Kubernetes, you deploy your service in terms of the pods, like containers which form pods. But you pay for something called node, which is basically an actual virtual machine, actual instance. And typically you set up your cluster or node pool, and you specify which kind of nodes you want to have. For instance, in this case on the slide, we specified like nodes with 8 CPU and 16 GB of memory, and we may think that this is ideal node for our use case. But over time, there will be other use cases, other services, other teams, etc. And these nodes are no longer optimal. And there is a lot of wastage on the nodes because these pods cannot occupy the nodes in full. And you may decide, okay, let's kill other use cases and let's use one like node pool or like profile of the nodes for the given use case. But it's not a solution because as we see on the picture, we have one node completely wasted. And so how to solve this? To solve this, we need to dynamically allocate nodes depending on the workloads are running on the cluster. And there are solutions for this. There is open source solution called Carpenter. There are cloud-specific solutions, for instance, Gkey after Pilot, and they know that Azure have something similar already. Or there are commercial or multi-cloud solution, like the one they use called CastAI. CastAI works for us pretty well because in addition to like this basic offering that providing optimal nodes for the workloads, they have a lot of other knobs that we can tune. For instance, they can take into account commitments, they can take into account spot instances, etc. And in general, offering as low cost for our cluster as possible. And another trap that we want to discuss called network cost, or we call it cloud tax. Why we call it cloud tax? Because everyone wants the service to be available. And for service to be available, it must deploy it in multiple zones. But once it's deployed in multiple zones, the zones communicate with each other, and the traffic between these zones get charged. It's called nice traffic, and many cloud providers have like charging for the nice. And so like if we want the service to be available, we incur this tax. And for instance, let's take a look at this example. Let's say we deployed ScyllaDB in 3 zones, and each zone have 2 nodes. Assume we deployed this and we just taken the vanilla driver and started reading from the cluster. In this case, for the given traffic T, we will be charged for T nice. Because when we read from Scylla, we may cross the zone, and inside Scylla cluster, they also can cross the zone. So one obvious thing that we must fix is to use token-aware routing. In this case, we will not have this extra hop inside Scylla cluster, and so our nice will be reduced to 2/3 of T. But even smarter is to use token-aware routing plus zone-aware routing. In this case, we will be reading from the same zone as we are. And so in this case, for the given traffic T, we will not have any nice. So like the charge for the nice will be 0. What about writes? In writes, it's impossible to avoid nice because we need to replicate the data. And so assume that we learned everything from the reads case. And so we access to the node in our zone, the right node, but it still need to transfer data to other nodes. So like for the given traffic T, we will have 2T nice charged. We can trade this a little bit with availability. So instead of 3 zones, we can deploy still in 2 zones. It will be a little bit worse in terms of availability, but still better than single zone. In this case, for the traffic T, we will have 1.5 T nice. Or even better, instead of treating this cluster as a single data center, we can pretend that each zone has its own data center. In Scylla, data center is a pure virtual concept, so we can split these 6 nodes into 2 data centers, each having 3 nodes. What's better in this case is that it's still optimized to reduce the traffic between zones. So like it will try to cross data centers as low as possible. Or in other words, for the given traffic T, it will cross it only once. So we will be charged T nice. It's probably not possible to go even lower in this case, unless we want to deploy the whole cluster in a single zone. But we can think to switch cloud providers, because turns out not all cloud providers charge for the nice. And for instance, Oracle Cloud and Azure Cloud, they are not charging for the nice. And if you deploy Scylla in these clouds, you don't need to think about any of that. You can deploy the best case you want in terms of availability. In this case, like you can deploy in the 3 zones, and you'll still have 0 nice cost because it's not charged. So that was all about cloud traps, and we go to the most interesting part, is called compute optimization, and I will hand over to David.
Thanks, Ivan. I'd like to dive into some of the compute optimizations we've done to our feature store. So let's have a quick look at the architecture first. Firstly, the responsibility of the store, as I mentioned earlier, is to compute, store, and serve features for our recommendation system. It naturally divides into these 3 components. The compute is a number of Flink jobs which ingest event streams, process them to compute features, and sync them to our storage layer. The storage layer is a ScyllaDB cluster, and the serving layer is a distributed gRPC service responsible for caching and handling consumer requests. I won't talk about the compute part today, but if you're interested, Ivan actually did a talk at KubeCon last year, and the slides are linked here. So the database first. The first thing I'd like to mention is scalability. People tend to think that databases are not scalable, whereas the reality is they're not very elastic. I've seen databases being well over provisioned to manage tests, backfillings, or even holiday traffic months ahead. Distributed databases like Scylla are actually fairly scalable. Thanks to Scylla support, we scale our clusters up and down many times in the year to respond to seasonal variations and manage our costs. The key here is to always keep a buffer for unexpected events and scale in advance for known events. Although we don't use it in production yet, I'd like to give a special mention to tablets in Scylla v6. This is a really cool step towards increasing elasticity, and we're looking forward to migrate in the coming quarters. The second things I would like to talk about is workloads. A very common problem is workloads impacting each other, and the most common being writes impacting reads. This is an example of where we were in the early days of our feature store. As you can see, we had a nice baseline for read latency, but then we would start a backfilling job, for example, and latency would spike for some time, breaking our SLA until the backfilling's done. The common reaction to this, as I mentioned earlier, is to scale up. This is the dumb and easy solution, and also the costly one, not to mention that it doesn't always solve the problem. Another very common solution is to have dual data center setup, isolate read and writes. This is a pretty nice solution, but comes with the fact that you have to manage double infra, and on top often leads to underutilized resources. We can't have it all. It's about trade-offs. The ideal would be if we could manage the share of compute allocated to different workloads. Then we could tune our database to fit our requirements, and that's exactly what Scylla's workload prioritization offered to us. Workload prioritization is a really awesome feature of Scylla. The idea is very simple. Different workloads can have different service levels or share of compute. This is particularly great when you have consistent workloads, and this tends to be the case for reads and writes. Under the hood, this relies on the thread per core architecture of Scylla. Each core can be seen as a task processor, and though it's a single thread, it's still async. Tasks are queued and picked by the async scheduler, but there are multiple queues with different priorities, and these priorities are exactly what workload prioritization is about. This is a snapshot from our cluster. As you can see, it's very simple. We have a very high share of compute for serving because we have strong SLAs on the read pass, which is user-facing. And most of the rest goes to compute, like writing the features to the database. And we keep a tiny share for manual queries for debugging, for example. This enables us to have exactly what we want, meaning those two different baseline for latencies, one for compute, one for reads, with much lower latency for reads. And that allowed us to have the best possible serving for our feature. So talking of serving, as I mentioned earlier, our service is a distributed gRPC service. The vast majority of cost here is compute. I did put a note on the slides that network can also be a large chunk of the costs. We've done tons of work actually to minimize our interzone egress costs, this NISE that Ivan talked about earlier. I won't get into this today, but do keep an eye on your network cost if your cloud charges for them. For these compute-heavy services, once you are past auto-scaling, it's usually time to look into optimizing the application itself. The first advice is the Captain Obvious one: don't go blindly. We set up continuous profiling very early on. Nowadays, there's tons of tools available. Integration is super straightforward. If you see this screenshot, you might recognize the vanilla GCP profiler, which is literally 4 lines of code to add in Go programs. And this has really helped us on our quest to reduce costs. We've actually unlocked more than 50% reduction in compute by doing optimizations guided by continuous profiling. So let's dive into one of these. Who says gRPC says protobuf. One of the largest chunk of compute for us was proto-SERDI. 95% of our requests are cached, and our hottest path looks like this. Multiple entities are requested. We get most responses from cache, some from the database, merge them all, and respond. In other words, we deserialize, merge, and serialize again. This is costly because ultimately the only thing we're doing is merging, and we really don't care about the value of a particular feature at runtime, for example. The win here is the ability to do partial deserialization. So let's have a look at this. And to explain it better, I think it makes sense to start with a little primer on proto-encoding. A proto message is encoded as a series of key value records. If you're familiar with proto definitions, the key is this field number that you have to specify manually, and that has to be unique per field. The value is encoded depending on the type, and I put a screenshot here from the proto documentation. A very important spec for this partial deserialization is that repeated fields, which can be seen as like lists or vectors, are encoded as a sequence of records. And similarly, maps are under the hood implemented as repeated fields. I'll get back to this in a second. So let's start with a simple example. Here we can see we have an inner message containing one integer and an outer message which contains a string name and a collection of inner messages. We can look at the encoding of a small example with Protoscope and the records that are produced. If you look on the bottom right, we'll see the field 1 first with the name, followed by the repeated fields producing a record per item as expected. So how can we leverage this? The key is that strings and embedded messages like our inner message have the same encoding as bytes. This means that they're interchangeable from the perspective of SERDI, and deserializing bytes is just a copy. Now remember what we looked at in the previous slides. Repeated fields are just a sequence of records, so similarly a repeated string or a repeated message can be deserialized as repeated bytes. This means that we can perform many operations without deserializing individual elements. Here's what this looks like. On the right side, you can see now we have an alternate lazy version of our outer message where we skip the deserialization of all individual elements by deserializing them as bytes. Any outer message proto can be deserialized as a lazy outer message. In practice, this means that in deserialized form, you would get a list of serialized messages, so a list of bytes, which you can manipulate like any other list. That means you can delete elements, swap elements, or even append two lists without deserializing the individual elements. So back to our cache, we store serialized features proto per entity in the cache, and our response is basically a collection of features proto. You can likely see where this is going. With partial deserialization, we can now form our response without deserializing the cache response, and that's the big win. So question is, how big is this win? I actually wrote a simple benchmark to compare this naive and lazy merging. You can go check it out on this GitHub repo. As you can see, we have a proto message with a repeated message and a map. This is very similar to this outer message we had earlier with the addition of a map. The operation we're looking at here is merging two instances of this message. And by merging here, I mean concatenating the lists and the map. The naive version will deserialize the message fully, append the fields, and reserialize. The lazy version will deserialize the fields to repeated bytes, append them, and reserialize. So what's the result? The result is that the lazy version is 6 times faster and required a third of the memory allocations. This was really a major win for us. It reduced compute, which in turn reduced costs drastically. And as a bonus, it also improved tail latency on our service. So not only did we save cost, but we also improved the product as a result. And this partial deserialization trick is now used in many of our services and jobs because it's so powerful. So in conclusion, a lot of innovation came out of our cost-saving initiatives. innovations, and also design decisions. As I tried to represent in this quadrant, there's a very unhealthy way to look at cost savings by focusing on shortcuts, which tend to have a negative impact on your product. The key is to stay on the right side of this quadrant and aim for the sweet spot, saving cost while improving the product. Before we part, there's many things we could not cover in this talk. We've done a lot of work on the compute side, which I didn't talk about today, and in particular, real-time window counters or Flink autoscaling. If you're interested in any of the topics below, please feel free to reach out to one of us. Thanks a lot for watching.